Hubble's law. In 1929, Edwin Hubble plotted the recession velocity against distance from the Earth for galaxies on which this data was known, and this is roughly what he found. This shows that the more distant the galaxy, the greater the recession speed. This was the basis for the Big Bang theory. The data actually closely follows a straight line through the origin, showing that recession velocity is directly proportional to distance, or adding a constant of proportionality, we can say recession velocity is equal to a constant times the distance. This constant, h, is what became known as Hubble's constant. As you can imagine, finding the distance to a distant galaxy is not all that easy, and the figures have changed significantly over the years. Although the current value for Hubble's constant is approximately 65 kilometers per second per megaparsec. Now, 1 parsec is equal to 3.26 light years, a light year being the distance that light would travel in a year. This relationship here, recession velocity equals Hubble's constant times distance, is what is known as Hubble's law. It allows us to calculate the age of the universe. The fastest speed possible is 3 times 10 to the 8 meters per second, the speed of light, and we do see objects called quasars with approximately the recession speed of the speed of light. To find the maximum size of the universe, well, rearranging Hubble's law, we find that d, the maximum size of the universe, will equal recession velocity of the speed of light over the Hubble's constant. Putting in the figures, we've got 3 times 10 to the 8 meters per second as our maximum recession velocity, and our best estimate of Hubble's constant of 65,000 meters per second per megaparsec. This gives a figure of 4,600 megaparsecs. Now, 1 parsec is 3.09 times 10 to the 16 meters, giving a distance of 4,600 times 10 to the 6, because it's megaparsecs, times the number of meters in a parsec, giving a size of the universe of a whopping 1.4 times 10 to the 26 meters. This allows us to calculate the age of the universe. The fastest speed possible is the speed of light in a vacuum, 3 times 10 to the 8 meters per second, giving a maximum distance to an observable object from Hubble's law. If the recession speed, v, is the speed of light in a vacuum, over the Hubble constant, we get a maximum distance to an observable object of 4,600 megaparsecs. 1 parsec is 3.09 times 10 to the 16 meters, giving a maximum distance of 1.4 times 10 to the 26 meters. At the speed of light, this would have taken, well, using time is equal to distance over speed, with speed being the speed of light in a vacuum, the distance being 1.4 times 10 to the 26 meters we found here, the distance to the furthest visible object, gives a time of 4.7 times 10 to the 17 seconds, or 1.5 times 10 to the 10 years. Just going through the procedure without putting the numbers in, we've found that distance is equal to recession speed over Hubble's constant, but the distance would also be given by the recession speed multiplied by the time taken. Distance is equal to speed times time. And so combining these, we get the speed multiplied by the time is equal to the speed over the Hubble constant. Cancelling out the c's, we get that the age of the universe, t, is equal to 1 over the Hubble constant.